Have you ever wondered what lies on the other side of the universe? We can look deep into the dark void and see galaxies billions of light years away. We can measure the rate at which the universe is expanding and even guess what it looked like shortly after the Big Bang. Yet, no matter how far we peer, there is always a limit, an invisible horizon beyond which we cannot see. Let us explore what this truly means and what might exist beyond that veil. Does the universe stretch on forever into infinity? Does it wrap around itself like a giant loop? Or do we live in a strange bubble with a boundary that can never be crossed? When we think about space, it is easy to imagine it as a massive bubble with a clear edge, like the surface of a balloon or the end of a map. But for scientists, the reality is much more complex. Asking where the universe ends might not even be the right question, because the universe does not seem to have an edge in the way we expect. To understand why, we must reconsider how space itself functions. In our daily lives, most things have boundaries. A country has borders, a field has a fence, and a house has walls. But the fabric of the universe is not built that way. It does not sit inside a larger space, it is space itself. Asking where it ends is a bit like asking what is north of the North Pole. Once you understand the shape of the object you are discussing, the question itself loses its meaning. One possibility is that the universe stretches on infinitely. In this scenario, there is simply no end. No matter how far you travel, there will always be more space ahead. You could travel in one direction forever and never hit a wall or a boundary. The issue is not that the edge is too far away, but that it fundamentally does not exist. While humans struggle to visualize infinity, mathematically, it is a perfectly valid model. If space continues to extend without ever folding back on itself, it remains boundless and eternal. Another possibility is that the universe is shaped in such a way that if you travel in a straight line long enough, you eventually return to your starting point, much like walking in a circle. This sounds strange, but it is similar to living on the surface of a sphere. If you walk east on Earth and never turn, you eventually circle the globe and find yourself back where you started. From your perspective, you moved in a straight line the entire time. This happens because the Earth curves in a way that is hard to perceive while walking. Space itself might behave the same way. If the universe loops back on itself, it is what scientists call finite but unbounded. This means it has a limited size but still possesses no edge. There is no physical barrier where space stops, it simply curves back into itself. This idea is rooted in Albert Einstein's general relativity, which tells us that space can be warped and twisted. If the universe contains enough matter and energy, its overall shape might curve inward like a sphere. Because space is so vast, we cannot easily see this curvature, but over extreme distances, it would have a profound impact. Both possibilities, an infinite universe or a curved, looping one, are consistent with our current observations. The problem is that we can only see a limited portion of the whole. Light travels at a finite speed, and the universe has only existed for about 13.8 billion years. This means we can only see the regions from which light has had enough time to reach us. This area is known as the observable universe. We live inside a bubble of light, and while we don't know what lies beyond its edge, that edge is not the end of the universe, it is simply the limit of our vision. Therefore, we cannot be certain if the universe is infinite or closed. What we do know is that there seems to be no place where everything just stops. Galaxies continue to stretch out in every direction for as far as our telescopes can see, and the farther we look, the faster these galaxies appear to be moving away from us because the universe itself is expanding. When we point our telescopes towards space, we are not just looking across vast distances, we are looking back in time. Light travels at nearly 300,000 kilometers per second. When we see a galaxy a billion light years away, we are seeing light that was emitted a billion years ago. We see it as it was then, not as it is today. In a sense, looking out into the cosmos is like reading a history book written in light. This creates a limit to how much of the universe we can see, a boundary known as the particle horizon. This horizon marks the outer edge of the observable universe. However, this shell is not a circle 13.8 billion light-years across, it is actually much larger. Because space has been expanding while the light was traveling toward us, the galaxies that emitted that light are now much farther away. Due to this stretching of space, the particle horizon is actually about 46 billion light-years away in every direction, giving us a visible sphere with a diameter of roughly 93 billion light-years. Inside this sphere is our observable universe. Outside of it, the rest of the true universe likely continues, but we cannot see it and we might never see it. The particle horizon is not a limit of existence, but a limit of visibility. Within this boundary, we can study galaxies, stars, and gas clouds. We can look back to the early universe and catch a glimpse of the oldest light in existence, the cosmic microwave background radiation. This faint glow comes from about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely for the first time. But beyond the particle horizon, everything remains hidden. There could be galaxies and planets similar to ours, or perhaps entirely different structures, but as long as they remain outside that horizon, we have no way of knowing they exist. Furthermore, this boundary is constantly changing. As time passes, light from even more distant regions will eventually reach us, and our observable universe will grow. A galaxy that is invisible today might become visible in the future. However, there is a catch. The universe is not just expanding, it is accelerating. This means distant galaxies are being pulled away from us faster and faster. In fact, many of these galaxies are now receding at speeds exceeding the speed of light. This does not violate the laws of physics because it is space itself that is expanding, not the objects moving through it. This creates another limit called the cosmic event horizon. This horizon marks the distance beyond which events can never affect us. Light emitted from beyond this line will never reach us, no matter how much time passes, because the expansion of space will carry it away faster than the light can travel toward us. This is a one-way barrier. Once something crosses this line, it is lost to us forever. We are often told that nothing can travel faster than light, and while that is true for objects moving through space, the expansion of the universe follows a different set of rules. Space can stretch at any speed, and there is no upper limit. The farther a galaxy is from us, the faster it appears to recede. This relationship is described by Hubble's law, named after the astronomer Edwin Hubble. If the distance to a galaxy doubles, its recession speed doubles as well. Eventually, at a certain distance, this speed exceeds the speed of light. This distance is known as the Hubble radius. What this means in practice is that although those distant galaxies still exist, their starlight will never reach us. They are beyond the reach of any signal or future communication. It is like trying to run up a down escalator that is moving faster than you can climb. You will never reach the top. We live in a unique era where we can still see very distant galaxies, but there is an invisible countdown. Much of the light we receive now was emitted billions of years ago when those galaxies were closer. Today, many of them have already crossed the Hubble radius. If they were to emit new light right now, we would never receive it. Even though their old light is still arriving, our connection to them is fading. This effect is driven by the acceleration of the universe. In the late 1990s, scientists studying distant supernovae discovered that the expansion of the universe is not slowing down under gravity, but is actually speeding up. An unknown force called dark energy is pushing space apart at an increasing rate. If the universe continues to expand at this accelerated pace, there will come a day when most of the galaxies we see today will vanish from our view. This will happen gradually. Their light will be stretched to longer and longer wavelengths, becoming dimmer and dimmer until they fade away completely. In the extremely distant future, only the galaxies in our local group will remain visible. Everything else will have drifted beyond the horizon, leaving our corner of the universe in total isolation. Observations from the Hubble Space Telescope and satellites like Planck all point toward the same somber conclusion: the universe is not just getting bigger, it is flying away from itself. We are standing in a vast, emptying room, watching the lights of the distant stars slowly go out, one by one. Due to the continuous expansion of space, the actual distance of a galaxy we see as being 10 billion light-years away today is likely well over 30 billion light-years. If we were to calculate how long it would take for light emitted from its current position to reach us, the answer might be never. We are capturing a fleeting glimpse of its past, while its present self is already beyond our reach. As the universe evolves, the Hubble radius changes as well. Some galaxies may still be teetering on this boundary today, but in a few billion years, they will cross it. Their light will fail to reach us, and their stories, as far as we are concerned, will come to an end. When you look up at the night sky, almost every star you see with the naked eye belongs to our own Milky Way. Compared to the vastness of the universe, they are practically next door, only tens or hundreds of light years away. The true scale of the cosmos reveals itself only through powerful telescopes that collect light that began its journey long before the sun was even born. This ancient starlight, some of the oldest we can detect, comes from the very edges of the observable universe. Every time we capture an image of such a distant galaxy, we are peering deep into the infancy of the cosmos. Some of these galaxies formed just a few 100 million years after the Big Bang. As their light traveled across the expanding universe, its wavelength was stretched into longer, redder regions of the spectrum, a phenomenon known as redshift. The higher the redshift, the older and more distant the object. For decades, astronomers have pushed to see higher redshifts, getting closer and closer to the beginning of time. This led to the launch of the James Webb Space Telescope in late 2021. Designed specifically to observe infrared light, Webb can detect the early starlight that has been stretched out of the visible range. In its first year of operation, Webb discovered candidate galaxies with redshifts greater than 10, meaning their light has traveled for over 13 billion years. These galaxies, appearing as tiny, faint dots, formed when the universe was in its cradle, just 300 million years after the Big Bang. They are sparse and small compared to modern galaxies, but they prove that stars began to light up the darkness much earlier than we once thought. By analyzing this light, astronomers are learning how the first generation of massive stars lived fast and died young, scattering the heavy elements necessary for future planets and life. However, there is a limit that no telescope can cross. Before the first stars and galaxies appeared, the universe was filled with a glowing, opaque fog of hot plasma. In this dense state, photons could not travel freely, they were constantly scattered like a flashlight in a thick mist. It was not until about 380,000 years after the Big Bang that the universe cooled enough for atoms to form, allowing light to finally break free. This first burst of light is known as the cosmic microwave background, or the CMB. It is not the light of stars, but the afterglow of the Big Bang itself, filling every corner of space as a soft, uniform hum. Dedicated satellites like WMAP and Planck have mapped this background in exquisite detail, revealing tiny fluctuations in temperature, the seeds of future cosmic structures. The CMB is our most important window into the early universe, yet it also acts as a wall. We cannot see through it with light. It marks the limit of what we can detect using photons, leaving everything that happened before it shrouded in mystery. While the CMB shows us the distribution of matter in our local bubble of the universe at that specific moment, it tells us nothing about what lies beyond our horizon. Some scientists speculate that hidden messages might be buried within these patterns, signs of other universes bumping into ours, or regions where the laws of physics are slightly different. So far, however, no clear evidence of such outliers has been found. The background appears remarkably smooth, which might mean the universe is uniform far beyond our horizon, or simply that our instruments are not yet sensitive enough to see the differences. To understand why the universe is so uniform, scientists point to a strange event that occurred in the first fraction of a second after the Big Bang, known as cosmic inflation. During this period, space expanded at an exponential rate, far faster than the speed of light. In a trillionth of a second, space stretched from a scale smaller than an atom to something larger than a galaxy. This theory solves the horizon problem, the mystery of why distant parts of the sky have the same temperature even though they are too far apart to have ever exchanged energy. Inflation suggests that everything we see was once packed into a tiny, connected region where heat could even out before being suddenly flung across vast distances. Inflation not only shaped the smoothness of the universe but also left behind microscopic ripples that gravity later grew into galaxies and stars. Yet, it also had a startling side effect. It pushed much of the universe so far away that its light will never catch up to us. Some theorists believe that inflation is still happening in other regions, a concept known as eternal inflation. In this view, new bubble universes are constantly inflating and cooling, each potentially with its own unique laws of physics, while we are confined to our own bubble by the speed of light and the expansion of space. We continue to look at the CMB and the first stars, searching for any ripple or shadow that might hint at the infinite reality beyond our unseen horizon. In the framework of eternal inflation, our entire observable universe is just one tiny bubble in a never-ending sea of cosmic foam. While our bubble cooled down and allowed for the formation of stars and planets, the space between bubbles continues to expand at an exponential rate, forever isolating these realms from one another. This suggests that the horizon we see is not the edge of all existence, but merely the limit of our perspective. Beyond it, there may be countless other universes, some with galaxies and stars like ours, and others with forms of matter and energy that we can scarcely imagine. One of the great goals of modern astronomy is to find direct evidence of the ripples in space-time caused by this rapid inflation. These primordial gravitational waves are incredibly faint and buried under layers of cosmic noise, but capturing them would be a milestone in our understanding of how the universe transcended its initial state. This theory of inflation forces us to rethink causality itself. It implies that parts of reality are forever cut off from us, yet they leave their footprints in the uniform temperature of the sky and the large-scale distribution of galaxies. Even if inflation ended in a fraction of a second within our bubble, the process may still be unfolding in the distance, birthing new realities in a landscape often called the multiverse. The multiverse is like a vast patchwork quilt or an infinite ocean of bubbles. In our bubble, the laws of physics are finely tuned to allow for atoms, chemistry, and life. In another bubble, gravity might be so strong that everything collapses instantly, or light might behave in ways that make atoms unstable. This provides a potential answer to why our universe seems so perfectly adjusted for our existence. In an infinite sea of universes with random physical constants, it is inevitable that at least one would be hospitable to life. We simply find ourselves here because we could not exist anywhere else. However, the greatest challenge to this theory is that these other bubbles are, by definition, beyond our reach. We cannot send probes to them or even see them. Some researchers look for signs of bubble collisions, scars in the cosmic microwave background left by another universe brushing against our own in the distant past, but so far, the sky remains smooth and silent. Beyond the question of size is the question of shape. Space might not follow the simple rules of a flat room, it could be twisted and connected in ways that defy our intuition. One of the most fascinating ideas in cosmology is that the universe could be finite but have no boundaries, similar to a video game where walking off the right side of the screen brings you back on the left. In mathematics, this is the study of topology. Just as a coffee cup and a donut are topologically equivalent because they both possess a single hole, the universe might possess a global connectivity that we have yet to discover. One model envisions the universe as a three-dimensional version of a sphere. The surface of a sphere is finite in area but has no edge or wall. If our universe works this way, its volume would be limited, yet a traveler could move in a straight line forever without ever hitting a boundary. Other possibilities include more complex shapes like a three-dimensional torus, essentially a cosmic donut, or twisted shapes where space folds back on itself. Astronomers have spent years searching for circles in the sky, patterns in the cosmic microwave background that repeat in different directions, which would indicate that light has traveled all the way around the universe and returned to us from the opposite side. While no definitive evidence of such repetition has been found, the data is noisy, and the universe may simply be much larger than the portion we can currently see. General relativity tells us that mass and energy curve space. Depending on the total density of the universe, space could be closed like a sphere, open like a saddle, or flat like a sheet of paper. Current measurements suggest the universe is remarkably flat, but nearly flat is not the same as perfectly flat. On a sufficiently large scale, there may still be a gentle curvature that eventually brings space back to itself. This leads to the ultimate thought experiment: if you traveled fast enough and long enough in a looping universe, could you eventually see the back of your own head? Could you return to Earth from the opposite direction? While theoretically possible in a closed universe, the rapid expansion of space means the road is being stretched faster than any ship could travel. We are effectively trapped within our horizon, not by a physical wall, but by the relentless stretch of time and space. Whether the universe is an infinite archipelago of bubbles or a complex, self-connecting maze, these theories remind us that our everyday sense of direction and limits does not apply to the cosmos. Is infinity a physical reality or just a mathematical illusion? We continue to build better detectors and plan new missions, hoping that a tiny ripple in the cosmic background or a ghost image of a distant galaxy will finally reveal the true architecture of our home. That concludes our journey through the mysteries of the cosmic horizon. I hope these thoughts bring you peaceful dreams and a wonderful day ahead. We look forward to seeing you in our next episode.